The universe is not the tranquil void we often perceive. It is a roiling arena of cosmic fury, shaped by forces that challenge our very imagination. Imagine vessels of gravity so dense they warp the fabric of space-time, where the laws of physics as we know them begin to shatter. From the primordial spark of the Big Bang, 13.7 billion years ago, to the invisible currents of the dark flow, pulling thousands of galaxies toward an unknown destination, we are but a single breath in the expanse of eternity. Are you ready to look past the horizon and explore the edge of everything? Our voyage into the greatest mysteries of the cosmos is a journey we take together across this vast world. Though we are separated by immense scales of distance, we are all connected by the same curiosity about our place in the galaxy. I would love to know, what time is it for you right now, and which part of the world are you watching from? Please leave a comment below so we can see where our community of space explorers is gathering today. If you enjoyed this deep space exploration, make sure to like and subscribe to join us as we continue to uncover secrets from the very edge of the infinite. Our journey begins in a quiet corner of the cosmos, within a galaxy we call the Milky Way. It is just one of more than 100 billion such galaxies scattered throughout the observable universe. And our Sun is a single star among the Milky Way's own 100 billion. For a long time, we saw each star as a gentle point of light in the vast darkness, much like our own. We now have a more complete and more complex understanding. The universe contains forces on a scale that challenges our imagination, energies capable of profoundly warping the very fabric of space and time. This is an exploration of those hidden dynamics, a voyage deep into the nature of a black hole. At Cape Canaveral in Florida, a new chapter in our quest to understand these phenomena is about to unfold. Secured within the payload of a rocket is a telescope named SWIFT, whose purpose is to seek out some of the most challenging subjects for astronomical observation. Black holes are defined by their immense density, which generates a gravitational field so powerful that nothing, not even light itself, can break free. This inherent invisibility makes them exceptionally difficult to study, but on this day, scientific anticipation is high. With the launch, the SWIFT telescope begins its ascent, carrying with it the collective hope of researchers aiming to reach the very edge of our current knowledge. The fundamental challenge is how to observe an object that cannot be seen. The solution lies in detecting the energetic signatures these objects leave on their surroundings. SWIFT's instruments were specifically engineered to register intense flashes of high-energy radiation known as gamma rays. This type of radiation cannot pass through Earth's atmosphere, but in the vacuum of space, SWIFT has an unobstructed view. These gamma-ray bursts are the telltale sign that a black hole is being born, an event that occurs when a very large star ends its life in a brilliant cataclysm called a supernova. Such an explosion is so luminous it can briefly outshine entire galaxies. The driving force behind this entire sequence of events is gravity, the fundamental interaction that governs the structure of the cosmos. The conventional view of gravity was once of an invisible force projected across space by objects like the Sunday, but a revolutionary perspective offered a different explanation, suggesting that space itself is the medium through which gravity acts. For Albert Einstein, space was not an empty void, but a flexible, four-dimensional fabric he termed space-time. In his view, gravity is simply the curvature of this fabric caused by the presence of mass. Heavy objects create a depression in space-time, and other bodies moving nearby follow these contours, which we perceive as an orbit. This was a profound shift in thinking, especially when considering its most extreme implications. Scientists wondered just how distorted space-time could become, and they found the answer by studying a specific type of star, a red supergiant, with a mass more than 25 times that of our Sunday. A star of this magnitude has a lifespan of only a few million years, a mere fraction of our Sun's existence. Deep within its core, the immense pressure of gravity drives temperatures to over 1 billion degrees. This intense heat fuels nuclear fusion, converting lighter elements into heavier ones, from hydrogen to helium, then carbon, and all the way to iron. Eventually, the core becomes so massive that it can no longer support its own weight and collapses catastrophically. This implosion triggers a shock wave that blasts outward, tearing the star apart in a supernova, while the core continues to compress, burrowing deeper into the fabric of space-time and forming a black hole. When the cosmic dust clears, What remains is an object with perhaps 1,000,000 times the mass of Earth, yet concentrated into a volume 1,000,000 times smaller. A black hole represents a rupture in the continuum of space-time. As you approach one, gravity intensifies into an inexorable current, pulling you faster and faster toward a final boundary. This threshold, known in cosmological terms as the event horizon, is the ultimate point of no return. Once anything crosses this line, escape is impossible, a reality that holds true even for a particle of light. Black holes are the ultimate expression of gravity, and yet they appear to be remarkably widespread. Astronomers have confirmed the existence of dozens in our own galaxy and estimate there could be tens of millions more. But the story of gravity's power doesn't end there. A completely different class of black hole exists. By observing galaxies far beyond the Milky Way, astronomers have discovered that nearly every large galaxy hosts a colossal black hole at its core. A particularly striking example is the galaxy known as M87, which contains a black hole 4 billion times the mass of our Sunday. It has left an unmistakable signature on its surroundings, a brilliant jet of material being ejected at nearly the speed of light. To understand the origins of an object of this magnitude, we must travel back some 14 billion years to the dawn of the universe, just after the Big Bang. As the cosmos began its rapid expansion, matter and energy spread outward. Scientists use advanced supercomputer simulations to recreate these early conditions and learn how supermassive black holes came to be. These models can follow the slow, steady process by which the first galaxies formed. From the very beginning, gravity was the dominant force, drawing together the primordial clouds of gas. These were not gentle formations. As they grew denser, they also grew hotter. Over millions of years, they reached temperatures sufficient to trigger nuclear fusion, and the first stars ignited. These pioneering stars ended their lives in powerful supernovas, while their cores collapsed to form the first generation of black holes. Today, billions of years later, and across billions of light-years of space, the Swift telescope is scanning the sky for the faint light of these ancient supernovas. Its observations are helping us piece together the story of what happened to those primordial black holes. Astronomers believe that some grew to enormous sizes by migrating toward the centers of their host galaxies, where they consumed a rich diet of gas and stars. Other black holes became even larger when their paths intersected. Scientific simulations can trace the collision of two galaxies, a dramatic dance that unfolds over 2 billion years. As the two galaxies merge into one, the black holes at their respective centers also combine, forming a single, tremendously powerful object. The gas spiraling into this new entity gets caught in a cosmic traffic jam, heating up and erupting in ferocious waves. These blast waves from supermassive black holes can extend for thousands of light years, potentially sculpting the size and shape of the newly formed galaxy. They may also enrich it with something vital. Black holes could be a primary mechanism for seeding galaxies, with the heavier elements forged inside stars, elements like carbon, oxygen, and iron, the very building blocks of solar systems and of life itself. This raises a compelling question. What is the story of our own galaxy? To find out if the Milky Way has a supermassive black hole, astronomer Andrea Ghez and her team have spent more than a decade at the summit of Hawaii's Mauna Kea volcano. Working with the giant Keck telescope, Andrea is investigating a mysterious presence at the very center of our galaxy. She has identified a cluster of stars that are swirling around an unseen object, and she is carefully measuring their speeds and mapping their orbits. Her telescope is so sensitive it can penetrate the dense veil of the Milky Way, looking through 26,000 light-years of cosmic dust to get a clear view of the galactic core. At the heart of our galaxy, an unseen force is compelling stars into motion. The one orbiting closest to the center is being accelerated to incredible velocities, reaching speeds of 3 million miles per hour. From this motion, Andrea and her colleagues calculated that the object responsible must possess a mass nearly 4 million times that of our own Sun. This provided powerful confirmation that a supermassive black hole resides at the very core of the Milky Way. The intriguing detail is that Andrea's work verified its existence without any direct visual evidence, leaving us to imagine what such an object would be like if we could see it up close. We can now embark on a virtual journey to this behemoth at the galaxy's center. While no physical spacecraft is planned for such a voyage, we can simulate the experience, guided by the most recent telescopic data and sophisticated computer models. Our expedition begins in the galactic suburbs, our home system located roughly midway from the core. From this vantage point, the full expanse of the Milky Way unfolds. Its sheer scale is difficult to comprehend. Light itself requires 100,000 years to travel from one edge to the other. Our destination is the galaxy's central hub, a dense sphere of stars referred to as the bulge. As we move inward from our relatively quiet neighborhood, the environment becomes increasingly crowded. Ahead lies a chaotic congestion of stars, dust, and superheated gas, a perpetual cosmic rush hour. Nearing the absolute center, the path is littered with evidence of past violence, including the remnants of supernovae and turbulent clouds. Our route to this point has been mapped by astronomers like Andrea, who chart these celestial landmarks by observing them across the entire electromagnetic spectrum, from radio waves to X-rays. Yet, their data reveals a strange void just ahead, an inner region seemingly swept clean by the immense gravitational influence of the object we are approaching. A disk of intensely hot gas orbits the central object. The black hole's gravity draws this material inward, though a significant portion is violently ejected back into space. What follows is a scientifically grounded visualization, not a creation of cinematic fantasy. It marks the first time researchers have modeled this journey, using Albert Einstein's equations as their guide. His theories predict that space-time here is so profoundly curved that the black hole itself behaves like a massive cosmic lens, bending and distorting the light from everything around it. We finally pass the event horizon, the threshold from which escape is impossible. Contrary to what one might expect, the interior is not a dark void. Instead, it is a swirling maelstrom of matter and energy. Concealed within this turmoil is the singularity, a single point where the entirety of the black hole's immense mass is compressed. If we could imagine a calm center within this storm, a place where the more exotic predictions of Einstein's theories could manifest, we might find a theoretical passage. This escape route through space-time is known as a wormhole. Traveling through it could lead to what is called a white hole. Here, the physics are inverted. Rather than pulling everything in, a white hole would violently expel all matter and light. The destination of this expelled material remains a question. Such a wormhole provides a convenient plot device for a fictional character seeking a rapid journey to a different universe. The reality, however, is that the interior of a black hole is likely far too turbulent for a stable wormhole to ever form, much less for anyone to traverse. It represents one of nature's most extreme forces, a destructive power on an unimaginable scale. And yet, this may be a limited perspective. It could also be seen as a fundamental process in a dynamic cosmos. In its youth, long ago, powerful outflows from this very black hole may have distributed essential elements throughout our galaxy. These elements could have been crucial in the formation of stars like our Sun, the planets that orbit it, and eventually, beings who could gaze at the heavens and ponder the nature of a black hole. Our quest to understand these phenomena continues to reveal both profound mysteries and brilliant new insights, uncovering secrets from the very edge of the infinite. We now turn our attention to planet Earth, to explore the intricate mechanisms of its global climate, the vast system that sustains life. We will investigate what makes our world so hospitable, and what led to the very different fate of our planetary neighbor, Venus. This is a journey into the winds, the oceans, and the natural forces that define our dynamic world. Consider the Earth as a complex machine, an interconnected system of components driven by the energy of the Sun. This machine, however, arrived without an instruction manual. How does it function? What are the fundamental processes of this elaborate system we call planet Earth, and what makes it so uniquely suited for life? To find out, scientists are using a fleet of satellites, piecing together how our world works. The clues they seek are scattered across the atmosphere, within every ocean, on each continent, and even in the distant reaches of our solar system. Like any machine, the Earth is composed of its constituent parts. These elements were forged in the distant stellar furnaces of our galaxy. When massive, ancient stars reached the end of their lives in supernova explosions, they enriched the Milky Way with heavy elements like iron, calcium, and potassium, the very building blocks of our bodies. Yet, these same events are believed to flood the galaxy with deadly, high-energy particles. Our solar system has a safeguard against this radiation. Our own star, the Sun, generates a protective bubble that extends past the orbit of the farthest planet, a field of influence that deflects the majority of these cosmic rays. However, the solar wind itself can be hazardous, particularly during violent eruptions known as coronal mass ejections. To see a vision of what can happen to a planet without adequate protection, we need only look to our neighbor, Venus. Over time, solar storms have scoured away the lighter elements from its upper atmosphere, including hydrogen and oxygen, and by extension, the water molecules they create. All that remains is a toxic mixture of chemicals, shrouded in thick clouds of sulfur. Closer to the surface, the Venusian atmosphere is saturated with immense concentrations of carbon dioxide. Since CO2 is an extremely effective greenhouse gas, it traps the sun's heat, transforming the planet into a furnace. Surface temperatures there reach nearly 500 degrees Celsius, making Venus the hottest planet in our solar system. The question then becomes, how did Earth escape a similar fate? The answer becomes visible as a solar storm nears our world. Earth possesses its own protective bubble, a strong magnetic field, which is generated by the motion of molten iron deep inside its core. This, however, is only the first layer of our planet's defense. A great deal of the solar energy that penetrates this shield is simply reflected back into space by clouds, ice, and snow. The portion of energy that Earth does retain is precisely the amount needed to drive the extraordinary engine of our planet, its climate. This engine is set into motion by the uneven distribution of solar heat across the globe, a result of the daily cycle of light and dark and the progression of the seasons. This imbalance causes warm air from the tropics to flow toward the poles, while cold polar air moves toward the equator. These vast atmospheric currents, in turn, are what drive the currents on the surface of the oceans. A computer simulation can illustrate this process, showing the Gulf Stream as it makes its way along the North American coastline. This immense river within the ocean transports a staggering amount of thermal energy, enough to meet the power demands of the entire industrialized world 100 times over. It eventually dissipates into enormous eddies that distribute warm tropical water throughout the northern seas. There, beneath the surface, these waters begin to mix with colder, deeper currents. Flowing across undersea ledges and around submerged mountains, the countless moving parts of Earth's climate engine are in constant motion. Tides and terrain, crosswinds and currents, all collaborate in a planetary effort to equalize temperatures across the globe. But when an overabundance of tropical warmth accumulates, that energy can be unleashed with tremendous force. In August 2005, from a massive looping section of the Gulf Stream, the ocean gave rise to a monster, Hurricane Katrina. A supercomputer simulation of the hurricane provides scientists with a powerful tool for better understanding the dynamics of such a system. To visualize the movement of air into the storm, they introduce a series of virtual streamers. The lighter colored ones represent warmer winds, which produce clouds as they rise and meet the cooler air above. The escalating winds enhance the evaporation of warm seawater, a process that pulls more and more heat from the ocean. This infusion of energy causes the winds to accelerate further, spiraling around the storm's eye at speeds that can reach up to 250 kilometers per hour. The sheer power of a hurricane like Katrina is difficult to comprehend. Every 20 minutes, it can release an amount of heat energy equivalent to a 10 megaton nuclear bomb. While storms are a mechanism for releasing heat stored in the ocean, the moisture they circulate into the atmosphere plays a crucial role in keeping the wider planet warm. Water vapor, along with carbon dioxide, effectively traps solar energy. This is the same greenhouse gas that contributed to the ruin of Venus. What sets Earth apart is its remarkable ability to regulate this atmospheric CO2, a process we can witness by journeying down to the ocean's surface. The special ingredient that distinguishes our world is life itself. The oceans are teeming with it, though much of it is too small for our eyes to see. Here, we find what might be the most vital organisms on Earth, phytoplankton. They absorb the carbon dioxide that is driven into the ocean by wave action or drawn up from the depths by currents. As part of their life process, they release oxygen while incorporating the carbon. From there, the carbon begins its journey up the food chain. Phytoplankton are consumed by zooplankton, a diverse group that includes radiolarians, which date back over 500 million years to a time when life first exploded throughout Earth's oceans. Another group, the copepods, are tiny bug-like crustaceans with more than 20,000 known species, making them the single largest source of protein in the sea. Moving up in scale, we encounter a host of creatures smaller than a fingertip, such as these octopus larvae. They are eaten by small fish, which in turn are prey for larger ones, like jacks. These are then consumed by the sea's largest predators, including orcas, tuna, and sharks. At every step along this food web, the carbon that started as a diffuse gas in the atmosphere is passed on and concentrated within progressively larger animals. The larger the body, the greater the mass of carbon it holds. One creature, in particular, takes this to an extreme. A humpback whale consumes up to 1.5 tons of food each day, representing an enormous amount of carbon. From the immense whale down to the microscopic phytoplankton, marine life is an integral part of a global system that removes CO2 from the atmosphere and then gradually releases it back. The true elegance of this carbon cycle, however, lies in our planet's capacity for long-term storage. A NASA satellite, calibrated to detect chlorophyll, offers a view of the global biosphere in action. This chemical tracer for plant growth shows how, in sync with the seasons, plants absorb vast quantities of carbon dioxide and release the oxygen we depend on. On land, this carbon can eventually make its way into the ground as plants and animals die and decay. The Earth itself participates in this process. When it rains, exposed rocks absorb CO2 from the atmosphere and erosion carries it into the oceans. If that carbon becomes part of the marine food chain, the resulting carbon-rich matter can sink to the very bottom of the sea in the form of organic waste. Countless organisms, like the salp, a jellyfish-like creature about the size of a thumb, live and die each year. All of this waste, all of those bodies with their stored carbon, rains down upon the ocean floor. Over immense timescales, these layers of carbon-rich sediment can transform into oil or into rock, such as limestone. This stored carbon can be returned to the environment as CO2 if the rocks are later exposed, or if they are forced deep underground by the movement of Earth's crust in the process known as plate tectonics. There, pressure and heat gradually intensify until the Earth erupts. Every year, volcanoes spew over 100 million tons of carbon dioxide into the oceans and atmosphere. Operating on timescales that range from a single day to millions of years, the carbon cycle has been instrumental in making our planet habitable, but its continued success is deeply intertwined with life itself. We are, in a sense, how the Earth works. If this intricate cycle were to go wrong, one might wonder what our world would become. The answer lies a world away, on Venus. There, the CO2 that erupts from volcanoes has nowhere to go. Venus is like a house engulfed in flames, with all the windows permanently sealed. The cause can be partly traced back to the destructive solar winds that scoured the planet. Shielded from those same winds, Earth has maintained a balance, absorbing and releasing CO2 in roughly equal measure. Recently, however, that equilibrium has begun to shift. The quantity of carbon dioxide originating from human activities including cars, power plants, and factories now surpasses the output of all volcanoes by a factor of more than 200. A significant portion of this comes from burning oil and coal, fuels that had stored carbon within the Earth for millions of years. Since the Industrial Revolution, the concentration of CO2 in the atmosphere has risen by nearly 40%, with the majority of that increase occurring in just the last 50 years. The consequence is that global temperatures have climbed by almost 1 degree Celsius. This is enough to accelerate the melting of vast ice reserves on high mountains and across the polar regions. Beginning in the 1980 seconds, NASA scientists began a systematic survey of the Arctic's seasonal shifts. Their findings reveal that the region has lost a quarter of its summer ice cover. What remains has also become dramatically thinner. This is merely the start of a series of changes that could reshape our world. Some regions may experience more rainfall while others face drought. Deserts could expand. Natural fires may become more common. Wildlife habitats could shrink, and polar regions might even become forested. As the ice melts, it drains into the oceans. By the end of this century, sea levels are now projected to rise by as much as 1 meter, threatening to inundate coastlines all around the planet. As our influence on the climate has grown, so too has our perspective. The view from space has allowed us to take stock of the elaborate, interconnected systems that protect and sustain our world. Within this intricate dance of wind and water, of time and tectonics, our planet has cultivated another extraordinary participant: life. Today, we find ourselves as masters of a world that is revealing itself to be ever more wondrous than we had previously imagined. And as we continue to explore its complex workings, we must ask ourselves a fundamental question: is our purpose to spend this Earth or to save it? There are cataclysms so immense, so planet-altering, they have rewritten the history of our world. Mass extinctions, the collapse of climates, and widespread toxic chaos. Witness Earth and the solar system at their most extreme. The Earth we perceive is merely a thin veneer, a placid surface that masks a colossal power churning below. Hidden from view, an immense fury is slowly building. The scene is set 74,000 years ago on the island of Sumatra, situated along the eastern perimeter of the Indian Ocean. Here, the signs of deep unrest were becoming apparent. Seismic tremors vibrated through the landscape, while vents began to open across the mountainsides, releasing sulfurous gases. The fitful slumber of a geological giant was nearing its violent end. A vast mass of molten rock was ascending, and as it pushed upward, cracks in the crust provided pathways for its escape. Lava and superheated gas began to pour out. This volcano, known as Toba, had erupted on 3 prior occasions over the last million years, but this event would earn it the rare title of a supervolcano. Seething from a crater that stretched for nearly 100 kilometers, Toba filled the skies with giant columns of smoke and debris. Over the course of 14 terrifying days, it ejected almost 3,000 cubic kilometers of ash and rock, an amount 1,000 times greater than the 1,980 eruption of Mount St. Helens. It stands as the largest volcanic event our world has experienced in at least 25 million years. The eruption draped a thick blanket of ash over a region half the size of Europe, while a dense layer of soot and smoke lingered in the upper atmosphere, obstructing sunlight for the years that followed. Toba's grim legacy was a global cataclysm. The planet was plunged into a volcanic winter, with average temperatures falling by as much as 10 degrees Celsius. Across the tropics, a drought took hold that may have persisted for 1,000 years, a time when the only thing that rained was falling ash. Scientists believe the consequences of Toba's fury reached our own ancestors as far away as Africa. In the dark years immediately after the eruption, their food sources would have dwindled, leading to a dramatic collapse in their population. The Toba catastrophe may have driven the human species perilously close to the brink of extinction. The answer to what causes such an event begins with our planet's birth, some 4.5 billion years ago, in a swirl of cosmic debris left over from the Sun's formation. Gravity drew together clumps of rock and dust in the chaotic early solar system, and through countless collisions, these objects fused. Each impact generated immense heat, and under this constant barrage, a fiery young world took shape. While its surface eventually cooled as the frequency of impacts decreased, its interior remained intensely hot. To this day, heat energy continues to rise from deep within the planet, a vivid reminder of the primordial fires that still burn. This internal heat escapes in part through volcanoes, particularly along the Pacific Ocean's outer rim, a region known as the notorious Ring of Fire. To understand the furnace that powers these volcanoes, one must look inside the planet. Heat travels upward through the vast middle region called the mantle, punching through the crust where it is thinnest, such as in the middle of oceans. This process drives the massive surface plates apart. Along the Ring of Fire, these oceanic plates collide with thicker continental plates, forcing them to thrust downward into the Earth. As they descend, they carry with them volcanism's secret ingredient, water. Certain rocks, when mixed with water, melt at lower temperatures, forming the reservoirs of magma that can fuel a volcano. It is this elaborate chain of events that Toba carried to an extraordinary extreme. As the molten rock and debris are blasted into the sky, the entire volcanic mountain range can collapse, creating an immense, cauldron-shaped basin. Water and heat remain the primary agents of change for a world that is still a work in progress. And Earth is not the only world shaped by this process. Welcome to Triton, an otherworldly moon of Neptune where surface temperatures hover at -235 degrees Celsius. This is no environment for flowing lava. Instead, volcanoes of water ice shower the landscape. On Triton, it is the geysers that qualify as super, capable of blasting liquid nitrogen at nearly 700 kilometers per hour to an altitude of 8 kilometers. On Jupiter's moon Io, some volcanoes have plumes of escaping gas that soar 500 kilometers above the surface. If on Earth, they would rise higher than the International Space Station. The power behind Io's eruptions looms nearby, as Jupiter's massive gravitational pull exerts a constant tug on the moon's core, generating incredible heat. Much of this energy vents through the largest known volcano in the solar system, named Loki, which may have formed when an ancient impact punctured Io's thin outer crust. Traces of volcanic activity also exist on Mars, Venus, several moons of Saturn and Jupiter, and in the distant past, even on our own moon. Yet it is Earth that may bear the deepest scars. The most destructive volcanic event in our planet's history occurred in what is now Siberian Russia. Rewind the clock 250 million years, to a time when all of Earth's land masses were fused into a single supercontinent known as Pangaea. This was the end of a spectacular geological period called the Permian, an era when life on Earth was incredibly prolific. Amphibians and early reptiles flourished, including the ancestors of both dinosaurs and mammals. Forests and swamps saw an explosion of insect species, while ferns, dominant for eons, began to yield to conifers and palms. The oceans were also brimming with life's bounty, where a wide variety of invertebrates and fish thrived amid vibrant coral reefs. It was Earth in all its glory. Then, in what amounts to a geological blink of an eye, it was over. An event known as the Great Dying caused up to 70% of all species on land and 90% of all marine species to disappear. Ecosystems across the planet collapsed in this mysterious blight. Scientists now believe a broad plume of rising magma pushed toward the surface. While the energy of such a formation typically dissipates as it spreads, here its many channels are thought to have erupted in unison, creating a single, sprawling supervolcano. It was hell on Earth. A series of eruptions generated 1,000 times more lava than Toba, choking the atmosphere with carbon dioxide and methane. Global temperatures soared, and the oceans turned acidic, their waters depleted of oxygen. The planet belched deadly toxins, including high levels of mercury. Throughout our planet's history, eruptions on this scale have been thankfully rare, but the question of whether one could happen now has an answer hidden in plain sight. Visitors to Yellowstone National Park in Wyoming may not realize they are standing atop one of the world's largest active volcanoes. Its legacy is etched into scenes like the fabled Yellowstone River. Heat from below softened layers of volcanic rock, which were then gouged out by a catastrophic flood at the end of the last ice age, carving a spectacular canyon. All around, the thermal energy is palpable, like a pressure cooker gathering steam, escaping in smoldering vents across the landscape. At Yellowstone, the Earth reveals its inner heat through a remarkable thermal display. Water erupts in magnificent geysers, reaching hundreds of feet into the sky, while ancient hot springs, rich with sulfur, perpetually simmer close to boiling. To understand this spectacle, one must trace the water's journey downward from the surface. It percolates deep into the ground, filtering through fissures in the rock below. About a kilometer down, this water encounters layers of superheated stone, compelling it to rush back toward the surface with immense force. Deeper still, at a depth of 10 kilometers, lies the upper boundary of a colossal plume of magma. This vast reservoir measures over 100 kilometers in width and extends 400 kilometers down into the mantle. Over the past 18 million years, Yellowstone has experienced repeated, massive eruptions. Several of these events seem to have been initiated by the same sequence that triggered the Toba eruption: a sudden, large-scale release of magma, followed by the catastrophic collapse of the overlying land, giving birth to a supervolcano. While some consider Yellowstone to be overdue for such an event, it is equally possible that another eruption may not occur for hundreds, or even thousands, of years. In the meantime, scientists maintain a vigilant watch, monitoring for the subtle precursors, the tremors, the rising ground temperatures that signal the restless movements of a planet under immense pressure. The familiar sight of geysers like Old Faithful serves as a constant reminder that the planet will, one day, again release its profound internal energy. Supervolcanoes are exceptionally rare, yet the power that creates them is a fundamental and ever-present force. What science suggests is that when the next one awakens, life across our world will be irrevocably altered. The great rivalry between the Soviet Union and the United States in the mid-20th century spurred an era of unprecedented technological progress. The space race accelerated the development of computers, satellites, advanced materials, and powerful missiles, innovations that reshaped modern society. Yet its most enduring legacy might not be a piece of technology at all, but rather a collection of stones gathered by astronauts from the lunar surface. These precious samples would ultimately provide a completely new understanding of Earth's formative period and the enigmatic origins of our own moon. As the most luminous object in our night sky, the moon has for millennia governed the cadences of life and inspired our deepest myths. It has also been a crucial stabilizing force in our planet's history, steadying Earth's axial rotation and, through its gravitational pull, generating the tides that drive the ocean currents, shaping our global climate. But concealed within its brilliant glow was one of science's most persistent questions. Where did the moon come from? At the dawn of the space age in the 1950 seconds, three main theories competed for acceptance. One idea proposed that the moon was once a part of Earth itself, flung into space by the rapid spin of our young planet. A second theory envisioned the moon as an interstellar traveler, a wandering body that was captured by Earth's gravitational field. The third hypothesis suggested that the moon simply formed in orbit alongside our own world. To resolve this debate, scientists in both the Soviet Union and the United States dispatched fleets of unmanned probes to the moon. These missions captured images, took measurements, and even made hard landings on the surface, but a definitive answer remained elusive. To truly settle the question, it became clear that humanity needed to walk upon the lunar landscape, to see it firsthand, and to bring a piece of it home for analysis on Earth. This scientific quest, however, was inseparable from the intense political competition between the two superpowers. The contest for space began in earnest on October 4th, 1957, with the Soviet Union's launch of Sputnik, a satellite that flew higher and faster than anything before it. The simple beep transmitted by Sputnik served as a profound wake-up call for the United States, directly leading to the formation of NASA and a national mission to put an American in orbit. The Soviets then delivered another surprise with Sputnik 2, a craft 6 times more massive that carried a living passenger, a dog named Laika. On April 12, 1961, they achieved another historic first when a Soviet spacecraft carried cosmonaut Yuri Gagarin into orbit around the Earth. Between 1957 and 1965, the Soviet space program consistently outpaced its American rivals. To surpass this lead, President John F. Kennedy proposed a goal of breathtaking ambition. He committed the United States to the objective of landing a man on the moon and returning him safely before the decade was over. Such a grand undertaking was fraught with difficulty. The Gemini program was established specifically to develop the technologies and master the complex skills required for a successful lunar mission, a process that involved its own share of setbacks. At the same time, the Soviets were pursuing their own lunar landing with the colossal N-1 launcher. It was a machine of immense complexity, featuring a first stage powered by 30 separate engines, all of which had to ignite and perform in perfect synchronization. Testing of the N-1's various stages commenced in 1968, leading to 4 full-scale, unmanned launch attempts. The American lunar effort, meanwhile, placed its trust in the powerful Saturn V rocket. The first crewed launch of the Saturn V was the Apollo 8 mission, which successfully carried its capsule and crew all the way to the moon and into lunar orbit before returning safely. With this achievement, a landing on the moon was finally a tangible goal for both nations. On July 13, 1969, the Soviets launched Luna 15. It was the third in a series of sophisticated robotic missions intended to land on the moon, analyze the lunar soil, and returned samples to Earth. Just 3 days later, Apollo 11 began its historic journey. Luna 15 reached lunar orbit on schedule, but controllers on the ground kept the craft circling as they performed final checks of its onboard systems. Then, on July 20th, 1969, Neil Armstrong and Buzz Aldrin started their descent toward the lunar surface in the lander, named Eagle. During the final approach, a series of computer overload alarms forced the module to fly past its intended landing zone. With fuel running critically low, Armstrong took manual control, skillfully navigating over a field of boulders as large as houses to find a safe place to set down. After a tense silence, the message came through that the Eagle had landed. About 20 minutes later, the two astronauts were outside on the surface. It was just as the American crew was completing their first historic moonwalk that Luna 15 finally began its own descent. But within moments, all communications with the Soviet probe were lost. The prevailing belief is that it impacted the side of a lunar mountain. While Neil Armstrong's first step was famously described as a giant leap for humankind, it was what he and the astronauts on 5 subsequent missions collected from the surface that would become Apollo's most profound scientific legacy. On these missions, they explored a world preserved in time. With no atmosphere to cause weathering, the rocks, dust, and craters of the moon held a pristine record of events, stretching back nearly to its very formation. As the astronauts walked and drove across the lunar terrain, scientists back on Earth were examining the moon with a new perspective. They observed, for instance, that some of the largest and oldest impact craters were encircled by a series of concentric rings. These features are clearly visible in a modern image of a formation known as Mare Orientale, which was captured by NASA's Lunar Reconnaissance Orbiter, where colors are used to represent differences in elevation. This observation led researchers to a new and intriguing hypothesis, that these rings could only have been formed if a massive object had splashed down into a surface that was still molten. This single insight gave rise to a revolutionary new idea about the moon's origins. In its earliest days, the moon was a global ocean of molten rock. When astronauts first walked its surface, they discovered that it was littered with relatively light rocks, a finding that suggested a process where heavier materials had settled toward the lunar core, forcing this lighter crust upward. But inside these rocks was a more profound clue to the moon's beginnings. Their composition was remarkably similar to that of Earth's rocks, sharing specific forms of oxygen that act like a unique fingerprint or a kind of blood type for bodies in the solar system. This evidence gave rise to a compelling new narrative for how the moon was formed. The theory proposes that early in the solar system's history, a planet-sized object about the size of Mars, which scientists named Theia, shared Earth's orbital path. Eventually, its orbit destabilized, sending it on a collision course with our young planet. Theia struck Earth at a glancing angle, a cosmic impact that dramatically increased Earth's rate of spin and blasted a tremendous cloud of debris from both Theia and Earth into space. As the dust settled, this material began to coalesce in orbit around Earth, gradually forming the moon. In the intense heat of this event, volatile elements like water were vaporized and lost to space, which helps explain why the moon is primarily composed of material from the mantles of both Earth and Theia, making it less dense overall than our world. From that violent conception, the moon slowly cooled, and the ocean of magma that covered it hardened into a solid crust. Even so, it remained a target in the turbulent environment of the early solar system, enduring an era of intense bombardment. The Apollo astronauts also found evidence of a secondary consequence of these impacts: rocks born in the crucible of widespread volcanism. On Earth, volcanic activity is often driven by water, superheated and pressurized by the movement of vast tectonic plates, but lunar volcanism is linked to impacts so powerful they could melt the surface and allow material from the hot interior to well up. When this occurred, molten rock flowed out in thin, smooth sheets that traveled great distances from their source. This is the process believed to have formed the vast dark plains known as the Maria, which cover roughly 1/6 of the entire lunar surface, relics from a period of large and violent impacts between 3 and 4 billion years ago. It now seems that these impacts made an even deeper impression on the moon's structure. One recent study attempts to explain the moon's lopsided appearance, the stark contrast between the dark lava basins of the near side and the cratered highlands of the far side. It posits that another, much smaller moon formed alongside our own at the time of its birth and eventually merged with it in a slow-motion collision. The force of this merger would have fundamentally rearranged the moon's interior, pushing molten magma toward the near side while simultaneously adding an extra layer of crustal material to the far side. The Apollo astronauts took the first step in exploring the lunar interior by deploying a network of seismographs. More recently, scientists followed up on this work by performing a kind of celestial CAT scan of the moon with a pair of spacecraft called Grail, which were designed to orbit the moon in perfect unison. By measuring minute changes in the distance between the two probes, researchers could map subtle variations in the moon's gravity. What they discovered was that the moon's gravitational field is not smooth, but is instead pocked with regions that exert an unusually strong pull. The Grail science team has now linked these anomalies to dense concentrations of mass buried deep within the moon, which correspond to the locations of large impact sites, such as the Mare Orientale Basin. The legacy of lunar impacts appears to be even more remarkable. In the year 2009, the LCROSS probe, which had travelled to the moon aboard the Lunar Reconnaissance Orbiter, was set on a collision course with the lunar South Pole. It slammed into a crater, and just seconds later, a trailing spacecraft observed a faint cloud rising from the point of impact. Analysis of this plume revealed that 5.6% of the crater's floor was composed of water ice, most likely delivered by comets that struck the moon long ago and had survived for eons in the permanent shadow of steep crater walls, shielded from the light of the sunday. And it now appears that this may be just the tip of the iceberg when it comes to vast, hidden reserves of water. While circling the moon repeatedly, a Russian-built instrument called LEND aboard the Lunar Reconnaissance Orbiter has found signs of hydrogen and possibly water ice embedded in the lunar soils far beyond the polar craters. And now, the rocks brought back by the astronauts are telling an even deeper story. Using new analytical techniques, several teams of scientists have recently detected a compound called hydroxyl, a molecule similar to H2O, but with only a single atom of hydrogen. Based on this finding, scientists now estimate that there is enough water locked away inside the moon to cover its entire surface with a layer 1 meter deep. The intimate connection between the Earth and the moon seems to trace all the way back to their shared origins, and so far, we have truly only scratched the surface of their intertwined history. The quest to understand that relationship was once a feature of the intense competition of the Cold War. Today, a whole new race to the moon is gathering momentum, this time fueled by the search for valuable minerals and metals, a pursuit of mining and money. Russia, the United States, China, India, and Japan all have missions in various stages of development, including a number of crewed missions, and a variety of private missions are also on the drawing boards. What will these new endeavours tell us about our celestial partner and the story of its formation? Inevitably, the more we learn about the mysterious birth of the moon, the more we will understand about its mother planet, Earth. Earth is a water planet. Its vast, interconnected bodies of water, the oceans, cover 71% of its surface. They regulate the global climate, and they fuel the powerful storms that drench the land, feeding the lakes and rivers that sustain us. And now, scientists have detected what amount to entire oceans of water hidden within the rocks deep inside our planet. How did our world come to be blessed with such an extraordinary abundance? Is Earth the only oasis in the vastness of space? For as long as humanity has gazed at the stars, they have offered few clues that somewhere beyond our solar system, another world as rich and diverse as our own might exist. Recently, however, astronomers have been discovering planets at an astonishing rate, using orbiting observatories like NASA's Kepler Space Telescope and sophisticated ground-based instruments. These alien worlds range from enormous gas giants, many times the size of our own Jupiter, to the rocky, charred remnants of planets that were burned when their parent star exploded. Some follow wild, elliptical orbits, swinging far out into the cold of space before diving in close to the scorching atmospheres of their stars. And yet, amid these often hostile realms, a few worlds bear faint hints of water or ice, the very ingredients needed to nurture life as we know it. The race to find these worlds is on. The discovery of worlds beyond our own reignites a profound question. Is our galaxy teeming with planets like Earth, making life a common phenomenon, or is our world an exceptional sanctuary in a largely sterile cosmos? To begin unraveling this mystery, we must look to our own planet's past, exploring the specific conditions that gave rise to its vast reserves of water. Far beyond our solar system, the seemingly empty expanse of space is in fact saturated with atoms and molecules. These fundamental particles serve as the raw materials for an evolving universe, the very building blocks from which stars and planets are formed. In certain regions, vast clouds of gas and dust, known as nebulae, radiate with the ethereal light of nearby stars. These are the cosmic nurseries, thousands of which are dispersed across our galaxy, where new stars and planetary systems come into being. Inside the frigid depths of these nebulae, atoms merge to create more complex molecules, including ammonia, methane, carbon monoxide, and water. For astronomers, the discovery of H2O is entirely expected. Its key component, oxygen, ranks as the fifth most plentiful element in the cosmos, and traces its origins to a specific type of star that often illuminates these clouds, the red giant. Within the intense heat and pressure of a red giant's core, hydrogen and helium atoms are forced together, forging heavier elements such as oxygen. When these massive stars eventually perish, they disperse oxygen and other newly created elements into the interstellar medium. It was from just such an enriched environment, approximately 5 billion years ago, that a medium-sized star, our Sun, ignited. From the swirling disk of gas and dust that encircled this nascent star, a complete solar system of planets, moons, asteroids, and comets slowly coalesced. Today, evidence of water can be found in nearly every region of our solar system. On the distant fringes, Pluto and its moon Charon belong to a category of small bodies that are remnants from the planetary formation era. Their surfaces are coated in a thick mantle of frozen methane and water ice. Moving inward, the striking blue hues of Neptune and Uranus are not due to surface water, but rather to methane clouds in their cold, dense atmospheres. Deep inside these ice giants, however, circulating charged particles within a vast sea of liquid water are thought to generate powerful electrical currents and magnetic fields. This internal ocean is likely a highly corrosive fluid, bearing little resemblance to the water we know. The iconic rings of Saturn are composed of innumerable particles of ice. Orbiting nearby is the moon Enceladus, whose pristine, icy crust reflects so much sunlight that it stands out as one of the most brilliant objects in the solar system. An intriguing discovery by the Cassini spacecraft revealed plumes of water ice erupting from its southern polar region, leading scientists to theorize that they originate from a subsurface liquid ocean. Jupiter, the solar system's largest planet, also holds its own reserves of water. While present in only modest quantities in its atmosphere, this water vapor plays a role in driving colossal storms, including the famous Great Red Spot, through a cycle of rising and falling moisture akin to thunderstorms on Earth. Past Jupiter's turbulent atmosphere and its volcanically active moon Io, we find another compelling world, Europa. Its remarkably smooth, bright surface is etched with a network of channels and grooves, believed to be fractures in an ice shell, covering a vast ocean of liquid water, or slushy ice. The moon is thought to possess an internal heat source, generated by the friction of Jupiter's immense gravity, constantly flexing its rocky core. If any life exists in this hidden European ocean, it would almost certainly be in a very basic form. Closer to the Sun, the asteroid belt is populated by what appear to be jagged fragments of rock and iron, yet even these objects contain trace amounts of frozen water. Remarkably, ice can even be found on the scorched planet Mercury, preserved within polar craters that are permanently shielded from the sun's intense rays. In a similar discovery, spacecraft have identified significant deposits of ice at the poles of our own moon. Furthermore, analysis of lunar rocks returned by the Apollo missions suggests that the moon's interior may also be rich in water. Then we come to Mars, situated at the outer boundary of what is often called the habitable zone. The planet receives enough warmth from the sun for liquid water to have once existed, a conclusion supported by the presence of extensive networks of ancient, dried-up riverbeds. Despite this evidence of a wetter past, modern Mars is a cold, arid world. During its summers, powerful dust storms sweep across the surface, while its winters see the landscape coated in a frost of frozen carbon dioxide. Any remaining water on Mars is now thought to be locked away in minerals beneath the ground. At the inner edge of this same habitable zone lies Venus, a planet remarkably similar to Earth in its size, mass, and makeup. But its dense cloud cover conceals a hostile environment. These clouds precipitate droplets of sulfuric acid, not water, onto the surface. While some sunlight penetrates the atmosphere, the thick blanket of carbon dioxide traps most of the heat, creating a runaway greenhouse effect. This process has made Venus the hottest planet in the solar system. Any water that might have existed there could not endure. Observations from the Venus Express mission revealed that the solar wind continuously erodes the atmosphere, carrying away the lighter hydrogen and oxygen molecules. These particles are stripped from the planet's night side and swept out into space. It's a process that may have also contributed to the transformation of Mars. So what accounts for our planet's profoundly different outcome? One critical factor is Earth's protective magnetic field. Generated by the motion of molten iron deep within its core, this field acts as a shield, deflecting the constant stream of charged particles from the solar wind. Unlike the case on Venus, this protection has allowed the water Earth acquired from the primordial solar nebula to persist on its surface for billions of years. Today, water in its three states, solid, liquid, and gas, is a defining feature of our world. It is locked away as ice in the polar caps, which expand and contract with the changing seasons. It circulates through vast oceans, lakes, and rivers that cover 3/4 of the globe, and it drifts through the atmosphere as clouds of water vapor. When solar radiation reaches our planet, this atmospheric vapor absorbs a portion of the energy, helping to retain warmth. Another vital component of our atmosphere, the trace gas carbon dioxide, functions as a planetary thermostat. It traps just enough heat to maintain global temperatures at a level that keeps water in its liquid and gaseous forms, preventing the climate from descending into a deep freeze or escalating into extreme heat. This delicate atmospheric balance, however, was not an initial feature of our planet. In its turbulent youth, Earth was covered with volcanoes that spewed enormous quantities of carbon dioxide and other gases into the sky. Over long stretches of geological time, a portion of this CO2 was drawn out of the atmosphere through chemical reactions with rocks and water, eventually being carried into the oceans. This process set the stage for another transformative development. Deep within the seas, early life forms emerged, possessing the remarkable capability to consume carbon dioxide and release oxygen through photosynthesis. This reveals a deeper truth. The mere presence of water is not sufficient for a planet to become like ours. The capacity to regulate key elements like carbon, cycling them between the atmosphere, the land, and the ocean, appears to be just as essential. For a distant world to be truly considered a counterpart to our own, perhaps the most profound challenge it must overcome is the ability to sustain a stable global climate. Over vast stretches of time, we have gradually learned to navigate our own water-rich planet, but the instruments of discovery have evolved. Today, our explorations are no longer confined to our homeworld. We now turn our gaze upward, toward the cosmos, seeking planets that echo the qualities of Earth. The fundamental questions drive this search. Do other aquatic worlds exist beyond our solar system? And could they possibly harbor life, whether familiar or entirely alien? Some compelling clues have already begun to surface from studies of distant stars, such as Kepler-62, located some 200 light-years away. Using data from the Kepler Space Telescope, scientists have identified 2 planets orbiting this star, both only slightly larger than Earth. What makes this discovery so significant is that both of these worlds reside within their star's life-sustaining zone. We are left to wonder about their nature. Do they mirror Earth, with its protective magnetic field, its balanced climate, and its immense oceans? Or did they follow a different path, one similar to Venus, our planetary neighbor, which devolved into a barren landscape beneath a dense, superheated atmosphere? As our view extends across the immense distances of space and the deep expanse of time, our quest for life continues. Ever watchful for the unmistakable signatures of a world like ours, another oasis in the vastness of the galaxy. Since the dawn of the space age, humanity has dreamt of journeys to worlds orbiting other suns, of setting foot on strange terrains, and perhaps even encountering extraterrestrial life. What was once the domain of science fiction is steadily transforming into the realm of scientific fact. With each passing year, our catalogue of planets around other stars grows, revealing worlds that are often bizarre and inhospitable, but also a select few that show the potential for life. As we systematically scan the galaxy for these undiscovered planets, we learn more not only about the universe but also about our own place within it. Over the past 2 decades, the development of high-precision telescopes has given us the remarkable ability to peer into the intense glare of faraway stars and discern the faint presence of orbiting planets. A prime example is 51 Pegasi, a star much like our own Sun, situated approximately 50 light-years from Earth. It was here, in 1995, that astronomers, by observing minute variations in the star's light, confirmed the existence of a planet in its orbit. For the very first time in our history, we had definitive proof that our solar system was not unique. The world they discovered was immense, over 100 times the size of Earth, yet it followed an orbit remarkably close to its parent star. Its atmosphere is a blistering 1,300 degrees Celsius, and it completes a full circuit around its sun every 4 Earth days. The existence of this exoplanet challenged everything we thought we understood about how planetary systems form. Our own solar system started to emerge from a vast cloud of interstellar gas and dust around 4.5 billion years ago. Over millions of years, this enormous cloud collapsed under its own gravity, giving birth to the Sun at its center. The remaining material flattened into a rotating disk, where collisions between dust and rock eventually formed the inner planets. Farther out, where it was cooler, hydrogen and helium gas coalesced around dense cores, creating the gas giants Jupiter, Saturn, Uranus, and Neptune. The planet at 51 Pegasi, now known as a hot Jupiter, is situated far too close to its star to fit this established model. One leading theory proposes that it originally formed much farther out in the solar nebula and then gradually migrated inward over time. We still have a great deal to learn about worlds of this kind, but each new discovery brings us a step closer to a more complete understanding of planetary systems. Astronomers located this particular planet by looking for clues concealed within the light of its star. An orbiting planet exerts a gravitational tug that causes its star to wobble slightly. Here at our telescopes, the starlight is passed through a spectrograph, an instrument that separates light into its constituent colors, much like a prism. The output is a spectrum, which displays a pattern of lines unique to that star. As the star wobbles, these lines shift subtly back and forth toward the blue end of the spectrum as the star moves closer to us and toward the red end as it moves away. Modern instruments possess such extraordinary sensitivity that they can detect changes in a star's velocity as small as 1 meter per second, which is roughly the speed of a person taking a leisurely walk. Each complete wobble corresponds to 1 full orbit of the planet. Armed with their knowledge of gravity, astronomers can then use this data to estimate the planet's mass and its orbital distance. This, however, is not the only method for detecting these remote worlds. Consider the star HD 209458. Scientists had already identified a hot Jupiter there using the wobble method, but in 1999, this exoplanet was seen passing directly in front of its star, an event known as a transit. Astronomers observed that the star's brightness dimmed by a small but regular amount every 3.5 days. This dip in light was minuscule, only about 1%, but it was the clear signature of a planet completing an orbit every 3.5 Earth days. Because larger planets block more of their star's light, this transit method provided astronomers with a direct way to measure the exoplanet's physical size. The planet, designated HD 209458b, was found to be less massive than Jupiter, but approximately 30% larger in diameter. This means it is significantly less dense, or puffier, than any planet within our own solar system. That breakthrough led to the development of new techniques for analyzing an exoplanet's atmosphere. As the light from the parent star filters through the planet's atmospheric layers, the atoms and molecules present there leave a distinct chemical fingerprint on that light. In this case, instruments aboard the Hubble and Spitzer space telescopes detected sodium, hydrogen, methane, water vapor, and possibly carbon dioxide, a collection of molecules that, under different circumstances, could be associated with the presence of life. The transit method gives us tools that could, in theory, allow us to spot the biosignatures of life on a rocky, Earth-like world. From what we currently understand, life requires a specific set of chemical building blocks, including carbon-based molecules. When combined with an energy source, such as a star, and the presence of liquid water, the potential for life emerges. Around every star, there exists a region known as the habitable zone, where a planet receives just the right amount of energy for liquid water to potentially exist on its surface. The question then becomes, where should we focus our search for planets that have solid surfaces and temperatures conducive to flowing water? With literally billions of stars in our Milky Way galaxy, the options might appear limitless, but they can be narrowed down. Supergiants, for instance, are the hottest and most massive stars, but they are far too unstable and have very short lifespans, likely not providing enough time for life to develop on an orbiting world. They are also known to end their lives in cataclysmic supernova explosions that would completely vaporize any nearby planet. We can also largely discount most double or triple star systems, which constitute more than half of the galaxy. A planet being pulled by the gravity of two or more stars would likely have an orbit too unstable for life to gain a foothold, and the combined light from multiple stars makes detecting such planets even more difficult. This leaves us to consider red dwarfs, the most abundant type of star in our galaxy. They are considerably smaller and cooler than our Sun, and do not radiate a great deal of energy. While they produce far less light or heat, these stars live for extraordinarily long periods, far outlasting our own Sunday. A solar system around a red dwarf could therefore have billions upon billions of years to survive, and for life to potentially evolve. In the year 2009, astronomers announced the very first discovery of a rocky exoplanet found in orbit around a red dwarf star. The star, named Coro 7, hosts a world that completes a full circle around its sun in a mere 20 Earth hours. With surface temperatures estimated to be around 2,000 degrees Celsius, this extreme planet is likely covered in oceans of molten rock. These massive, rocky exoplanets, such as Coro 7b, are often categorized as super-Earths, representing some of the most unusual and exotic worlds ever detected. It is important to note that the term super-Earth does not imply any significant resemblance to our home world. The majority of those found so far orbit much too close to their central star, making them far too hot for life as we know it to survive. There is, however, one recently discovered solar system that may offer a more promising environment. The red dwarf star Gliese 581 is a relatively close neighbor to us, situated just 20 light-years away. A team of French and Swiss astronomers had been observing its light from a telescope high in the mountains of Chile. In their data, they noticed a very slight jitter in the star's position, the unmistakable gravitational tug of orbiting planets. Their analysis first revealed the presence of Gliese 581b, a planet with 16 times the mass of Earth, orbiting at a distance of only 6 million kilometers from its star, ensuring it would be intensely hot. Next, they identified planet C, about 1.5 times the size of Earth, with an orbit of 11 million kilometers. Its location, just inside the system's life zone, suggests it is also probably too hot. Then came the discovery of planet D, 7 times the mass of Earth, orbiting at 33 million kilometers from its sun. This world sits at the very outer edge of the star's habitable zone, where it receives only about 30% of the light that Earth gets from our Sunday. One could imagine a much larger version of Mars, a planet with a thin atmosphere, no liquid water on its surface, and average temperatures hovering around -59 degrees Celsius. Some astronomers even theorized that planet D might be an icy world that migrated inward from the outer reaches of its solar system. On the other hand, one can speculate on a different possibility. What if planet D possessed some of the critical attributes of our own world? What if it had geological activity that produced a substantial atmosphere, a large moon to stabilize its orbital tilt, and a powerful magnetic field to shield it from harmful solar winds? In the future, as our scientific instruments grow ever more sensitive, astronomers will carefully search for signs that this distant world has an atmosphere. Within that atmosphere, they will look for the chemical compounds that could be associated with life, such as methane, carbon dioxide, or water vapor. It is not entirely beyond the realm of possibility that we, or perhaps a robotic emissary, might one day be able to visit and see it up close. It is plausible that planets the size of Earth, and maybe even habitable ones, are commonplace throughout our galaxy. Given the immense distances involved and the overwhelming brightness of their parent stars, the primary challenge is simply in finding them. Until quite recently, our technology and detection methods were best suited for discovering massive planets. That, however, is beginning to change. Launched in 2009, the Kepler Space Telescope was specifically designed to look for Earth-sized planets located within the habitable zones of their parent stars. Kepler's mission was to precisely measure the light from 100,000 stars similar to the Sun, watching for the minuscule dips in starlight that serve as the telltale sign of an exoplanet transit. The mission has already discovered a remarkable array of giant planets, with orbits that last only days or weeks. In the years ahead, astronomers will continue to comb through their vast archives of data, searching for the faint signals of Earth-sized worlds with orbits of a year or more. As they continue this meticulous search, what emerges is a picture of a remarkable diversity of solar systems. Consider Kepler 1.1, located 2,000 light-years from Earth, which has 6 planets all larger than our own, packed into orbits smaller than that of Venus. The Kepler 2.0 system has 5 planets, 2 of which are about the size of Earth, but all of them orbit closer to their star than Mercury does to our Sunday. Then there is the case of Kepler 4.7, a double star system where 2 planets have been discovered so far. The innermost planet, the smallest detected by the transit method at the time, is 3 times the size of Earth, but it is so close to its stars that its year is only 50 Earth days long. Farther out, with an orbit of 303 days, Planet C is situated within the life zone of its stars. Unfortunately, this promisingly located world is a gas giant, slightly larger than Neptune. We continue to ask the fundamental question: are there worlds like ours somewhere out there in the cosmos? We now possess the technological capability, the powerful telescopes, and the advanced computers that will begin to help us find the answer. Whether we ultimately find that Earth-like planets are commonplace or exceedingly rare, there is one thing we know with certainty. Our world is but one tiny grain of sand on the beach of a vast cosmic sea. Looking in any direction we choose, the universe extends onward for incomprehensible distances. So far, billions of years have whispered by this small corner of the galaxy. Billions more years will transpire long after we are all gone. Our moment of life is like a single breath of air in the expanse of eternity. As we look up into the night sky, we wonder what new worlds await our discovery, and what light they will shed on the origin and evolution of our own Earth. While searching for new worlds, astronomers also peer deep into the universe, probing the clash of cosmic forces and the obliteration of matter and energy. We can glimpse the very limits of time and space in the strange and violent death of a star. There is perhaps no vision more reassuring than the endless cycles of the sun and the moon, the heavens ceaselessly turning above us. The night sky appears eternal and unchanging. Modern astronomy, however, has given us a much different vision, one of a universe that roils and vents its rage. That vision comes together in the death throes of a giant star. Its surface is a stormy sea of fire as superheated gas rises and sinks in massive convection cells. Giant waves form, creating solar tsunamis 1,000 kilometers high. Immense loops of hot, electrified gas, each one larger than the entire Earth, blast out into its atmosphere. Deep within its core, the star has begun to collapse in on itself. This catastrophic collapse causes the star to erupt in a violent supernova. In its wake, the explosion leaves behind a trail of colourful, glowing filaments and luminous, billowing clouds. Remarkably, the death of one star gives rise to a whole new generation of others. This profound cycle of death and birth has defined the history of our Milky Way galaxy, and that of billions of other galaxies across the universe. Our vision of space has been shaped by a handful of rare exploding stars, which were bright enough to be seen by the naked eye. In the year 1054, stargazers in North America spotted a supernova near a crescent moon. This same event was recorded by observers in China, Korea, and the Middle East. The astronomer Tycho Brahe saw one in 1572. He later wrote that he was led into such perplexity by the unbelievability of the thing that he began to doubt the faith of his own eyes. Johannes Kepler recorded the next one in 1604. Galileo used this very event to make his case for a whole new approach to astronomy, one based on the idea that change is a fundamental part of the cosmos. To find out how stars shape our world, we must look closer. To comprehend the universe, astronomers now command a remarkable suite of advanced technologies, from colossal telescopes situated on high mountain summits to an entire constellation of sophisticated instruments operating in the vacuum of space. When we gaze at the stars through a conventional telescope, we are perceiving the visible light that they radiate. What's fascinating, however, is that this sliver of light represents just a tiny fraction of the full electromagnetic spectrum. At one end of this spectrum, we find the short, high-energy wavelengths of X-rays and gamma rays. At the opposite end are the long, low-energy radio waves. Immense arrays of radio telescopes are currently being utilized to gather these faint radio signals originating from stars in the distant cosmos. Scientists employ these instruments to peer through the obscuring veils of nebulas and vast gas clouds, revealing the celestial objects concealed within. Meanwhile, at the other extreme of the spectrum, ultraviolet light, X-rays, and gamma rays offer a different window onto the universe. The very short wavelength of X-rays, for instance, is what allows medical professionals to pass them through our bodies and visualize bone fractures. In a similar way, astronomers search for these same high-energy emissions in space as they serve as telltale evidence of the most powerful and violent processes unfolding across the cosmos. The very forces that sculpt the universe on its grandest scales are visible in our own celestial neighborhood. Our sun is a star of average size, with a surface that maintains a temperature of nearly 6,000 degrees Celsius. Deep inside its core, conditions are far more extreme, with temperatures soaring to 15 million degrees Celsius. This combination of intense heat and immense pressure ignites the nuclear fusion reactions that transform hydrogen into helium, releasing a tremendous amount of energy in the process. The Sun, in common with all other stars, spends its existence in a constant battle against the inward pull of gravity. The outward pressure generated by the energy from its core successfully keeps its outer layers from collapsing. For a star like our Sun, there is enough fuel to hold gravity at bay for many billions of years. The situation is quite different for a much larger star. It burns through its fuel supply far more intensely and rapidly, continuously forging heavier and heavier elements within its core. Eventually, the core reaches a critical point where it can no longer produce sufficient energy to counteract the crushing force of gravity. At this moment, it undergoes a catastrophic collapse, which is immediately followed by a titanic explosion. Yet, destruction is far from being a supernova's sole legacy. The incredible blast disseminates essential elements like carbon, oxygen, and iron into the surrounding interstellar environment, the very building blocks required for life as we know it. The powerful shock waves emanating from this explosion can also act as a trigger, initiating the birth of entirely new stars. In fact, our galaxy is dotted with stellar nurseries that were set into motion by ancient supernovae. One of the most spectacular of these is the great, luminous cloud of gas and dust we call the Orion Nebula. It is here that astronomers have been able to identify nascent solar systems in the very act of formation. When clouds of this nature grow dense enough, the conditions for nuclear fusion are met, and from them, new stars and their planetary systems are born. A completely different destiny, however, awaits the remnant of the exploding star at the heart of this cosmic event. In the aftermath of the supernova, its incredibly compressed core can survive the blast intact. To visualize its density, one might imagine the entire planet Earth being squeezed down to the size of a tennis ball. This is a neutron star. Some of these objects can rotate at astonishing speeds, spinning hundreds of times every single second. When the first of these, known as a pulsar, was detected by radio telescopes, its remarkably regular signal was initially thought by some to be a transmission from a distant alien civilization. The famous Crab Nebula is the expanding shell of the very same supernova that was observed and recorded by multiple cultures on Earth in the year 1054. Deep within this intricate structure, scientists have located a pulsar and have documented how waves of its radiation have carved circular patterns into the surrounding gas. Some dying stars, however, are fated to become something stranger still. It seems that nature has devised a true monster of the cosmos. The scientist Albert Einstein once theorized about a star possessing such an overwhelming gravitational field that nothing, not even light itself, could break free from its grip. He ultimately dismissed this idea as a physical impossibility. Yet, what once appeared to be beyond the realm of reason now stands at the very frontier of modern science. Astronomers now understand that when a particularly massive star explodes, a sufficient amount of matter can collapse into its core, causing it to effectively vanish from the known universe. In this final confrontation, gravity wins the ultimate battle. From our perspective here on Earth, we typically define our universe by familiar standards, including the various forms of light found along the electromagnetic spectrum. Black holes, by their very nature, defy this method of discovery. The central question became, how can we possibly detect an object that emits no light at all? Astronomers found the answer in a brilliant flash of gamma radiation that appeared to come from the direction of our galaxy's center. Radio telescopes were quickly focused on this source, and what they discovered were jets of matter being ejected outward in two opposite directions. Their observations revealed a black hole siphoning a stream of gas from the outer layers of a nearby companion star. As this material spirals inward, it forms a rapidly spinning accretion disk. This disk generates powerful magnetic fields that become twisted and act as a conduit, channeling some of the inflowing matter away into a pair of high-energy beams, or jets. Astronomers now know that black holes can infuse these jets with so much energy that the material within them is accelerated to a velocity that is only a tiny fraction less than the speed of light. It was later discovered that this particular black hole, which is catalogued as GRA J165, 5-40, is hurtling through space at a staggering 400,000 kilometers per hour. This is 4 times faster than the typical stars in its vicinity. The most plausible explanation is that it was violently ejected, much like a cannonball, by the very supernova explosion that created it. Black holes, with their capacity to command such extreme energies, are more than mere cosmic curiosities. There exists a class of enormous black holes that trace their origins back to the earliest epochs of the universe, a time when the first generation of stars was forming at a furious rate. When these primordial giants reached the end of their lives, some of them gave birth to the first black holes. Gravity then relentlessly fed these nascent black holes a steady diet of stars and gas as matter began to coalesce into the first galaxies. As smaller galaxies merged to form larger ones, a select few of these primordial monsters grew to become billions of times more massive than our Sun. By launching their immensely powerful jets, they heated the vast regions of gas surrounding their host galaxies. This process effectively cut off the flow of gas into the central galaxy, which had the effect of stunting its growth and thereby allowing smaller, peripheral galaxies to form and evolve. But the influence of these colossal black holes did not end there. This image from the Chandra X-ray Observatory reveals a cluster of galaxies known as Hydra A. The cluster is enveloped by immense, hot cavities that glow brightly in X-ray light. A jet, visible in radio wavelengths, can be seen erupting from its central galaxy. An analysis of the gas along the edge of this jet revealed high concentrations of iron and other metals, which were likely forged in supernova explosions. By propelling these metals into regions far beyond their origin, the black hole effectively seeded more distant galaxies with the elements necessary for the formation of stars and solar systems, much like our own. Supermassive black holes can now be observed at the heart of nearly every large galaxy in the universe, and we have identified a growing number of them actively powering these massive jets. We are, in a very real sense, the beneficiaries of the violent and creative life cycles of stars, and yet we are also separated from these cosmic events by scales of distance and time that are far beyond anything we can experience in our daily lives on Earth. That profound separation is thrown into sharp relief when we consider the journey of the twin Voyager spacecraft. Launched in 1977, after completing their exploration of the outer planets and their moons, these remarkable craft are now navigating the farthest reaches of our solar system, tens of billions of miles from home. As it travels at 16 kilometers per second, The Voyager 2 spacecraft is on a trajectory that will bring it within 4 light-years of the star Sirius, though not for another 290,000 years. From our small vantage point in the galaxy, we have come to understand that stars do more than simply illuminate the cosmos. They are the very forges that seed the universe with the building blocks of life. When we observe the brilliant demise of a star, we are offered a brief look into the fundamental forces that not only give shape to the universe, but also transform worlds like our own. Since the dawn of civilization, humanity has wondered what lies just over the horizon, beyond the vastness of the oceans, and where the world truly ends. As we have ventured further and further outward, our journey has unveiled a solar system, then a galaxy, and then a universe on ever grander scales. Today, a new generation of theories suggests that the true scales of time and space are almost beyond comprehension, leaving us to ask what we might learn in our continuing search for the edge of everything. If you could somehow stand apart from our planet, what would you perceive? How do the sprawling deserts relate to the deep oceans, or the towering mountains to the wide floodplains? What cosmic architecture links the Earth to the other planets, the distant stars, and the realms beyond? The ancient Greek philosopher Aristotle conceived of a cosmos with the Earth at its very center, encased within a series of 55 celestial spheres. He believed each sphere moved in a precise way that could predict the locations of the planets and stars. For Aristotle, these outer domains were the dwelling place of the gods, and he described them as being composed of a pure, divine substance not found anywhere on Earth. Yet, the Greeks were also the first to begin viewing celestial events as natural occurrences that could be understood through human reason. One skywatcher, Anaxagoras, proposed that meteors were made of materials common on our own world and may have even originated from it. He and other Greek astronomers helped to lay the very foundations of science, but they would surely be stunned by the discoveries of their modern counterparts. The stars and planets that were once thought to house deities are now understood to be infinitesimal components of a vast scaffolding of matter and energy that stretches far into the depths of space. Aristotle's Earth-centered model of the cosmos prevailed until the 16th century, when Nicolaus Copernicus put forth a different idea, that the Earth and the other planets actually revolve around the Sun. Based on his observations of planetary orbits, scientists began to construct new models to describe their motions through time. An intriguing detail of Copernicus's work was his assertion that the firmament of stars was located far, far beyond the solar system, which began to expand our conception of the universe's size. This mental expansion accelerated in the year 1609, when the scientist Galileo Galilei pointed the first astronomical telescope toward the heavens. He observed that the Milky Way, the broad, luminous band that graces summer skies, was not a cloud, but was in fact composed of countless individual stars. In the centuries that followed, astronomers determined that our Milky Way is a vast, rotating disk. They envisioned the universe as a stellar island of stars and gas, immense, yet ultimately limited in its size. This model of an island universe, however, would soon be overturned by new scientific evidence. At California's Mount Wilson, working with the enormous new 100-inch telescope, astronomer Edwin Hubble and his assistant, Milt Hugh Mason, began to analyze the light from fuzzy patches in the sky, then known as nebulae. What they discovered was that these patches were not nearby clouds, but were entire galaxies in their own right, situated at immense distances beyond our own. They also made the remarkable finding that most of these galaxies are moving away from us. The farther a galaxy is, the faster it appears to be receding. This discovery gave rise to an entirely new model of the cosmos, one filled with countless galaxies within a universe that is continuously growing larger. The implication was profound, because the light from these distant galaxies requires millions or even billions of years to reach us. The deeper that astronomers peered into space, the further back in time they were able to see. To study the history of the cosmos, scientists built larger and larger telescopes to gather the faint light from the universe's most remote regions. They started to see that the stars, and the universe as a whole, were not as tranquil or as static as had once been imagined. In an era defined by nuclear physics and atomic weapons, a new vision of the universe emerged. It was a dynamic realm, actively shaped by giant exploding stars, powerful shock waves, and mysterious black holes. In this view, the universe began with a violent, primordial event, a Big Bang. The Big Bang model was built upon four principal observations. First, the universe is expanding in all directions, which suggests that if time were reversed, all matter and energy would trace back to a common starting point. Second, it explained the existence of light elements like hydrogen, which would have formed in the earliest moments and later been converted into heavier elements inside stars. Third, it predicted a faint glow of light pervading the cosmos, emitted when the universe was young and since stretched into microwaves by expansion. Finally, it established a coherent timeline for the evolution of stars, galaxies, and the large-scale structures of the universe. But even this new model of a Big Bang universe would prove to be incomplete. Recent precision measurements from the Hubble Space Telescope and other instruments have led to a consensus that the universe is 13.7 billion years old. When cosmic expansion is taken into account, galaxies at the very edge of the visible universe are now an estimated 46 billion light-years away from us in every direction. What lies beyond those galaxies, and how did the universe grow to such an immense size? Another observation puzzled astronomers. No matter which part of the sky they examined, the distribution of galaxies, the density of matter, and the background temperature are all remarkably consistent on large scales. To achieve this degree of homogeneity across its entire breadth, the universe would have needed to expand far more rapidly and to a much greater extent than the standard Big Bang model allowed. A new cosmic model, with a novel explanation for how the universe became so large and so uniform, was on the horizon. It emerged from one of the most important scientific observations of our time, connecting the universe we see around us to its very first moments. On the 24th of April 1990, the Space Shuttle Discovery deployed the groundbreaking Hubble Space Telescope into orbit. 5 months earlier, however, another, more modest launch had taken place. The Cosmic Observation Background Explorer, or COBE, was designed to capture the microwave light that was released when the universe was still in its infancy. This ancient light, the mission found, contained a subtle pattern of hot and cold spots. Later, the WMAP and Planck satellites updated this observation, recording the patterns in far greater detail. Within these slight temperature variations, scientists had found the very seeds of everything we see around us today. The universe was smooth on a grand scale, but on smaller scales, it was textured with the faint blueprint of all future structure. In an age of computer-controlled telescopes and automated observation, astronomers began a new quest to understand how the universe evolved from its earliest cosmic template. International collaborations were formed with the ambitious goal of mapping a significant portion of the visible cosmos in 3 dimensions. The celestial chart that has since emerged guides us on a journey outward from our own quiet corner of the Milky Way. We travel first through our immediate cosmic neighborhood, a gathering of about 20 galaxies known as the Local Group. Continuing some 50 million light-years farther, we approach the Virgo supercluster, a densely populated galactic city, the nearest of its kind. Beyond Virgo, the arrangement of galaxies becomes even more structured, forming immense walls and arcs. What stands out on the larger scales is that the universe resembles a vast cosmic web, composed of long filaments of galaxies that are bordered by enormous, empty voids. To explain the origin of these immense formations, scientists have put forward a more expansive model of cosmic creation. This model is founded on the discovery that energy is perpetually welling up from the vacuum of space, appearing as pairs of particles with opposite charges, matter and antimatter. The new concept, called inflation, holds that the universe itself sprang from these subtle fields of energy. It proposes they somehow shifted into a higher energy state, which caused space and time to inflate at a tremendous rate. Within this primordial energy, tiny fluctuations generated pressure waves, or ripples. As the universe continued to evolve, these ripples produced slight variations in the density of matter, which the force of gravity then began to amplify over cosmic time. To forge a link between these ancient ripples and the galactic patterns we see today, astronomers have used supercomputers to simulate the universe's evolution. These simulations begin in its early history, when the cosmos was just 10% of its current age, and they show matter steadily accumulating into denser and denser regions, where stars, then galaxies, and eventually galaxy clusters took shape. It's a crucial detail that simulations like these are designed to replicate only a fraction of the visible universe. The universe as a whole is now understood to be inconceivably larger. The full theory of cosmic inflation suggests that the universe expanded from the size of an atom to a cosmological scale in an infinitesimally brief period. In the billions of years since its birth, the theory posits that the entire universe would have grown to be some 10 billion trillion times the size of the observable universe, a number represented by a 10 followed by 24 zeros. To put this into perspective, the relationship in size between the whole universe and the observable universe is thought to be the same as the relationship between the observable universe and a single atom. As incomprehensibly large as the inflationary model suggests the universe is, that may not even be the limit. Our perspective has been expanding for centuries. 400 years ago, Galileo demonstrated that our sun is but one of many stars. 8 decades ago, astronomer Edwin Hubble revealed that the Milky Way is a single galaxy in a vast ocean filled with countless other island universes. More recent observations have continued to reveal ever greater scales, from the immense size of our galaxy to clusters of galaxies, and beyond them to the vast walls and filaments of matter. By relying on an underlying physical process to explain the birth of the cosmos, the idea of cosmic inflation has prompted scientists to think in far broader terms than ever before. There are, for example, versions of the theory which suggest that we live in just one of many universes, perhaps coexisting side by side like bubbles. In this view, these universes are continually emerging and expanding throughout an ocean of infinity. This idea represents a quantum leap in our sense of scale, extending our concepts of time and space far beyond our visible horizon. It leaves us with a profound question. Does this realization push us, on our tiny, out-of-the-way planet, into an ever smaller corner of creation? Or does our capacity to assemble models that describe the larger universe somehow elevate our importance in the grand scheme of things?